Thanks for coming. So, to bring you in the right mood for this talk, let's start with a beautiful beach. So just imagine you're on a beach, a cold breeze is coming in, you hear the waves, you're completely relaxed. It's a wonderful day until suddenly, well, actually, you're not on the beach, it's just a dream. You wake up in bed in the middle of the night, it's a very hot and stiff room, and your pager alert goes on because you're on pager duty. You get your pager on and, oh no, your production system is down with some error you don't understand. So you pull out your laptop, look on the screen, and some Chinese, some hieroglyphs, some C code that is also barely understandable. Oh no. So, this talk is going to be how to actually understand what's going on when you see something like that, but understandable. So, Petra already introduced me a bit. So, I'm from Hamburg, Germany. It's the first time I'm speaking at PyCon Czech Republic. Spoke at a couple of other conferences, DevConf in Brno. So, contributing to CPython, a couple of other projects. I'm also in professional time working for Red Hat as security engineers, working on software stacks, FreeIPA and DocTag. That's also related to authentication, authorization, and certificates. So, what's this talk actually about? Agenda and takeaways. So, first I'm going to introduce you to the history of SSL and TLS, give you a high-level overview what actually TLS is. Then I'm going to different kind of errors, so connection errors, a bit of crypto, how the handshake works, how the handshake code wrong, certificates, public key infrastructure, how that can go wrong related to creating the handshake, and finally, where do we actually get the trust for our certificates, and how host names are verified at the very end, before I give you a quick summary and some links and more resources. So, but first, actually, should we do TLS? Before I get into details, the short answer is yes. The longer answer is yes, you should, for multiple reasons. Actually, these days, it's very easy and cheap to get a certificate, so there's no more excuses that you have to pay lots of bucks for a certificate. It's also not as slow as you think. Actually, TLS had only one performance issue. It's not widely deployed. To give you one example, that actually TLS is much faster than plain HTTP. Here's from Troy Hunt. That's downloading lots of resources for web page, so JavaScript, images, whatever, CSS, over HTTP. It takes about 5 or more seconds. If you switch to HTTPS, it gets magically much, much faster. And the reason for that is HTTP 2. So if you deploy TLS, you get much more benefits. You can even tell your SEO people, your manager, you get better SEO from Google and other search machines, so Google bumps up everybody that uses TLS. You get the performance of HTTP 2, because HTTP 2 is not allowed to be transmitted over plain HTTP. It's only defined for HTTPS. And you also get a much better user experience, because these days browsers start to give users nasty warnings every time there's some kind of login prompt or even form. Well, there's really no reason to don't use TLS these days. So what's TLS, SSL? There's a couple of terms. The most important thing people confuse is 1 is bigger than 3, and 1.2 is actually hex code for 303. Yeah. Because there's SSL, there's TLS, and also something called start TLS. Well, I'll get you in a minute. So actual TLS is the successor of SSL. We have SSL1, which was never released. Had rumors was breaking during the initial meeting on paper. SSL2, SSL3 are rather old, and then the IETF came in and wanted to make a public standard, because SSL was only defined and created by Netscape back then. And so they thought, well, let's give it a new name, a new version number, and so TLS 1.0 is actually SSL 3.1. And there are a couple of more standards. The most recent is currently TLS 1.2, although 1.3 is probably coming out a couple of months, although they said the same a couple of years ago. So, but the draft is mostly finished and mostly implemented by OpenSSL and NSS, the library used by Mozilla and by Chrome, and yeah. So SSL is the old term that uses. TLS is the new word, although I still confuse it a lot because OpenSSL, SSL model in the standard library, yeah. But try to use TLS. And start TLS is actually also TLS, but something called opportunistic TLS. Instead of directly starting TLS, you do a normal handshake, talk about plaintext protocol, and at one point of the server, the client say, I now want to switch to secure communication, and they switch an existing communication channel to TLS. There are a bunch of TLS SSL libraries. The most relevant for us in the Python community is OpenSSL. There are also ReSSL and Boring SSL, which are forks. NSS use Firefox, the NSS. Microsoft and Apple have their own implementations, their own stack. And there are a couple of other ones, even one currently defined for inside the kernel, so kernel TLS, which is interesting, also a bit scary, but also interesting. There are also a bunch of Python libraries. So I maintain this SSL model, the standard library. There's PyOpenSSL, which is mostly used by Twisted these days because we didn't have the necessary bits and pieces in the standard library for async IO, and so we added async IO. Python NSS, we use that at Red Hat a lot. Are we also moving away from that? Corey Benfield, the one developers and contributors to Request in Rel 3, started to work a C-types binding to Apple's framework, and a bunch of more. And to give you a quick example how the SSL model works, it mimics lots of OpenSSL APIs. So you create first a context, either with that function or you do it manually. The function internally that creates default SSL context loads some default root certs and sets secure modes. And then you open a socket connection, and you use the context to wrap the socket into an SSL socket. And the SSOC here, you probably can't see that from behind. So SSOC here, that's a SSL socket that then does all the secure stuff. You send data over that. So, high-level view. Most people think TLS SSL is like this green checkbox, and also most people think that TLS is equal to encryption, but it's much more. To give you the Wikipedia definition, transport layer security are cryptographic protocols that provide communication security over a computer network. The TLS protocol aims primarily to provide privacy and data integrity between two communication computer applications. So it's a bit more than just providing encryption. In fact, besides encryption, it also provides encryption in a way that can tunnel most protocols. You can do HTTP, you can do LDAP, you can do Postgres, MySQL protocol, or whatever, email, IMAP, SMTP. It also provides integrity checks because encryption doesn't protect you against somebody messing around with the data. It protects somebody replaying your communication, so somebody can't record you sending money to somebody from a bank account and then replay the attack. If the attacker tries to replay that, it fails. It also identifies the server, so you know that you talk to your own bank and not some other site. Can also authentication on the other side, and it's a very extensive protocol built on top of a lot of different standards, which make it rather complicated to use if you have to go deep in the protocol stack, which we're now going to do because you want to understand what's SSL error and why does it occur. There can be multiple things coming together to cause an error, starting from just something on the network level going wrong, so there's DNS routing, you may just talk the wrong server, either on purpose because somebody's hacking you or something else goes wrong. TLS-SSL, just the handshake is very complicated because it's extensible, has lots of moving bits and pieces. There's lots of crypto involved. ASIN1 is a very funky, old, interesting protocol used both for public key infrastructure and SSL and certificates. Okay, connection. What happens if you connect to a web server over HTTPS? So to give you a quick rundown of a handshake, I'm going to elaborate on that later on. You'll see that slide a couple of times with more data filled in. So first of all, we have to do a DNS lookup to actually translate the host name to an IP address, and then do a TCP handshake to create a TCP connection. Next up, the client sends some kind of hello to the server. The server says, hello back, and then some other stuff happens until finally we have an encrypted channel, and we can actually send like an HTTP request. Connection issues can actually start with simple stuff. So if you run into any kind of issues connecting to an SSL server, I always start to first check if the connection okay. So that errors usually means DNS issues, either that you have a typo in your host name or DNS servers are down. Connection refuse can mean there's a firewall in between you, or you have to use a proxy to talk to your server. That one I'm going to explain later a bit because that's an interesting one. And also if the connection just blocks. You connect and nothing happens. Well, but okay. First of all, DNS. So if you have DNS issues, host command, dig command, you probably can't read that small text. These are two tools to translate a host name to an IP address. You also notice I'm getting both an IP44 and IP46 address, which means we can connect over both of them, and there's some internal magic to select the right protocol. To look up if your host actually is available, ping and trace route help. You can just send a ping and pongs back. And when you get a ping, you probably can't talk to the server. It's not, maybe your Wi-Fi is down. Well, you can use, if you create a connection, use a tool called TCP dump to listen on the network what's going on. Although it's a bit tricky because you have to specify the right interface. So that's interface loopback. And here's a rule. So that string here is the rule that, OK, give me only information back that's for host, localhost, and port 443. And then you see it first tries to connect to something IP46, the blue one. And next up, it tries something IP that's IP44, the old one. Yeah. So that's actually the socket create connection. So Python uses dual stack features to try to connect to both of the protocols. When that fails, or that succeeds, you don't get any further. Curl is actually a very useful tool. I can just put that on the screen. Because if you, no. Sorry. Here we go. So with curl, you get a lot of information, and if you call -v-s, you get exactly what's going on internally. So I use that also a lot to debug issues, but you probably won't understand what's going on until I explain the actual handshake. So just to show you that quickly, let's go back to my slides. No, I hate that. Here you go. Well, here we go. So there are multiple tools you can use just to debug the initial issues. So hostdict, ping, TCP dump, Wireshark, we'll explain later. What actually also helps, just scan the server and read the logs. Or what may be surprising, use your browser. Your browser can connect to something. It usually means it's okay, maybe there's another issue, and browsers are very useful to get debug information. So, TCP, TLS, handshake. So let's get a bit deeper. So we were able to create this TCP connection here. So we have the handshake drilled on, connected. So now we actually want to upgrade the TCP connection to a TLS connection. And for that, we send the hello. And the hello contains a couple of additional data that the server then uses to negotiate parameters. There's the cipher suite, so the cipher that your client knows just sends a huge list of all ciphers supported. It sends which maximum protocol version it can talk. These days, hopefully, TLS 1.2. Some random stuff, and a bit more, but I'll get to that a bit later. The server then uses that information to select a cipher suite, select a version, and also select some server random and sends back some more information, and yeah. So, even on that stage, the server may either not respond with a server hello or fail very early. So, that error I mentioned before that, either wrong version number or the connection just hangs if you talk to an HTTPS server. Often, not always, but in most cases, it just means, well, you're not talking to a server that can talk HTTPS. Maybe you misconfigured your web server and 443 actually is just plain HTTP, or you selected the wrong port, or maybe you have to use start TLS if you use LDAP. Yeah, so it depends a bit. Even some web servers do something, send you an error, and the protocol stack just failed. Sometimes doesn't respond at all. May also, if the server actually is talking TLS, respond with something called unsupported or wrong protocol, there are a couple of error messages. The SSLError alert, handshake failure, can mean a lot of things, which is really bad. Usually means there was an error establishing secure parameters. Any parameter can go wrong, but it doesn't tell you which parameter go wrong. So you have to make a good guess or use other tools. TLS alert protocol version often means that the server doesn't speak the protocol. These days, often if you have a client that cannot speak TLS 1.2, but the server wants TLS 1.2, sends that back. And if you get a strange error from SSL, maybe you're using the wrong protocol, so you use the server protocol to talk to a server instead of using the client protocol, so you use some wrong parameters for SSL context. So, SSL version 3 alert handshake, or error number 40 internally, can be no cipher suites overlap. So you send a list of cipher suites, but the server doesn't know any of the cipher suites or doesn't want to talk any of them. Maybe, again, unsupported version or some other parameters like curves and signature algorithms, but if that goes wrong, you need a bit more tooling. I'll get back soon. But cipher suites and unsupported version number, you can figure out, for example, with a tool called SSL scan, which gives you multiple pages of this long listing here. What the tool actually does, it configures a socket with a specific TLS version or SSL version and one cipher suite, tries to establish a connection, and sees which error the server returns. So here it tells me that it rejected some ciphers, other one failed. That usually means the server doesn't know that at all. That one means it doesn't like to talk that. Some were accepted, and that server I used Python.org refused all cipher except TLS 1.2 cipher that are these days marked as secure. So that tool can run rather long, can take like a minute or so. The server is very slow. Yeah. Cipher suites. So what does these things actually mean? Quick crypto rundown, because I can explain that. I'm going to run through that slides now, because on that section will take a whole talk to explain in detail. So to do a connection to secure that, you need some way of hashing something, so making a fingerprint of a long thing to a very short checksum. You need something to fast encrypt lots of data because you're going to use bulk encryption. Although you can't just encrypt easily, you need to use some kind of modes. Otherwise, you will see the structure of your document, so Linux Penguin. So there are a couple of cipher suits mode for block ciphers. Don't use ECB. The rest is usually fine, but depends on your use case. You need some additional things to create like verified connections and verify that nobody tampers with the connection. And there's a bit of asymmetric crypto magic also in there. So asymmetric encryption, signatures, or key agreement. Asymmetric crypto basically means you have like a private key and a public key, same with IKEA, and you keep the private key or the public key, and either you can use your private key to decrypt something that was encrypted with your public key, or somebody can use the public key to verify that your signature with the private key was okay. That's signing, the couple of algorithms. There's also third one called Diffie-Hellman key agreement, where you send your public key to somebody else. They send you the public key, and through magic and math, you agree on a common secret. Wikipedia explains that with mixing colors. Very good example. Yeah. And you need some other stuff to do TLS crypto, but again, they will take the whole talk. And you combine that in a cryptographic building blocks for a cipher suit. You notice different colors here. This long strings actually mix them all together to make something usable. So for example, elliptic Diffie-Hellman ephemeral mode used with elliptic curve DSA. Use AES for block ciphers, Gauss counter mode for the block operations, and SHA-384 for hashing something internally. There are lots and lots of cipher suits, a couple of hundreds. Most of them are barely usable, so you probably won't use null encryption with MD5 these days. It's frustrating is that OpenSSL decided to use different names than the official ones. So just to give you some names, these are the official ones, these are the OpenSSL ones, and yeah. But if you want to look at what's actually configured in OpenSSL, you can also use the SSL model starting Python 3.6 to take a closer look. So now we know a bit more about crypto. Let's look a bit deeper. So for the simple case, the old case, we would just send back the certificate chain after the hello. And then the client would encrypt some kind of session random with the public key of the server, send that back, and they both would use that to establish a common secret to do the actual bulk encryption. That's actually rather insecure, and also I tried to use that example, so the old one with Python.org, which kind of failed because Python.org has disabled it. Bad one. So I had to use badssl.com, which is a collection of websites that just contain bad examples for SSL. And so how many time have I left, Peter? Already 10 minutes. Well, I'll show you a good example, because that's going to be less time than I anticipated. Are you sure? I thought they had, well, okay. Don't argue with Peter. TLS hand exchange with RSA key is a bad one because it had no forward secrecy. So if an attacker would record all your transaction and somehow later get the private key by just stealing it or hacking it, then it could decrypt all the existing traffic. But with the new one, Diffie-Hellman, so using this color mixing scheme, you never ever transmit the secret, but through some kind of tricks establish a common secret, and the server verified that it knows the private key of its certificate by signing this parameter it sends back. And to show you how that looks on the wire, I'm going to show you another tool you can use to diagnose TLS SSL. Let's move that here. So that's a tool called Wireshark, which lets you exactly see what's going on and gives you very nice information about the protocol because it dissects the protocol in great details. So you see the client hello, sends some parameters like the cipher suit. It also sends the host name we want to talk to. And the server replies to that with some additional information and eventually sends a list of certificates back. And then the client finalizes that, and they both do change ciphers back. And yeah, that's a very useful, very powerful tool to diagnose TLS/SSL. And now I lost the. And I got to the wrong slides. Well, let me get to the right one. Oh, wait. We're here. So, yeah. So that's called ephemeral Diffie-Hellman key exchange, and that is mostly forward secret, except if you use session assumption, but that's going to be fixed in TLS 1.3. Yeah. Well, so during the key exchange, we also got a list of certificates back from the server, and that list of certificates is what establishes the identity of the server. So the bank gets a certificate from some trusted entity to explain, okay, I'm really that bank, I own that URL, I own that domain, and you can trust me, I'm the right one. But somehow it has to actually verify that, and you have to be able to verify that the certificate belongs to the bank. And that's handled with public key infrastructure and certificates. And that's mostly the biggest pain point, what can go wrong if you do SSL handshake. Protocol rarely goes wrong, except if you have old client and modern server or the other way around, but that one is a big pain point. So, the official name of certificates is called X509 certificates. It uses ASN1 also for data structures. It usually comes in a pair of a certificate and a private key. And it contains the public key and several additional data. And one tool to look at the certificate, I use that very often as OpenSSL command tool client, X509, which is a bit weird to use because you say text, but don't give me any output. But that combination will give you just the text output, but not the actual certificate output. Well, and if you look at certificate, it looks a bit like that. So you have a version, it's usually 3 these days. You have a serial number that is tied to your certificate. So every certificate gets a new serial number. Somebody has issued the certificate, so that's a CA. It also has like a range how long it's valid. It has a name, and it holds some public key. That's the public key to your private key. It also has a bunch of extensions, like some key usage, extended key usage. That means it can be used to authenticate a web server. It's not a CA, also very important. These kind of strings are used for chaining. I will explain that in a minute. There's also the access information, where it can get additional information, and there's the actual name, and then it's signed by a CA. So, how they work? You have a root CA, that's the trust anchor, that's usually stored in your browser or your operating system, and you have a couple of intermediate CAs, because the root CA keys are secured in a vault. And then you have an end entity certificate, so for a web server, for example. And when you make a TLS connection, it sends this whole chain to you. Root CA has specific flag, usually no No path length restriction. The intermediate CAs are really restricted, so you have like a CA that is only allowed at the end to sign actual server certificate and not create a new part of the chain. And then you finally have the end entity certificates, which have this key usage explaining, yeah, it can be used for servers or it can be used for clients or for both. And for the PyCon.dz website, that's the chain collected a couple of days ago, uses Let's Encrypt, and you see you have this entity certificate, you have another one, and then it stops. So it doesn't send that one because that one is actually installed in your browser. And if you want to get a bit more, you can also pipe the output of S-Client into X509, OpenSSL tool, yeah. Extended, just side notes, just this extra green bar is just another field in the certificate. There's nothing special about the cert except for an additional field. And also, please protect your private keys. And now the interesting bits, when that goes wrong, because that's the most hard thing to debug. And if you have Python 3.6 or 2.7, yeah, I'm sorry, you don't get more information than that. So you have to use the command line tools from OpenSSL to get information. So that's using also bad SSL with an expired certificate. And at the end, you see, OK, certificate is expired. What can go wrong here? So yeah, can get expired. Also maybe not yet valid, which usually means that your clocks are wrong on your system. There's a bit of trick, so you have to have the right key usage. That was an issue I had with my own certificates. It took me a full day to figure out. I forgot to add the digital signature bit, and that means I couldn't use Diffie-Hellman key agreement. So DS is used for Diffie-Hellman, key encipherment is used for us a handshake. If you don't have the right bits, it doesn't work and gives you very, very weird error messages. The chaining failure, so if you fail to verify the chain, is even more tricky. So some error messages common is self-signed certificate. Usually means you didn't use a proper cert, just a test cert. If you get the error message unable to verify, then it means you didn't send the full chain, only the end entity certificate. Browsers have a way to figure out the whole chain on their own. They use some information in the fields to download additional certificates from the internet. Python can't do that, so you have to submit the full chain. Unable to get local issuer certificate usually means you didn't configure your root CAs. And if you have a self-signed one, usually means the same, except the server also sent the root CA, which is allowed to do, but doesn't make any sense. So any kind of that, you actually have to use some tools to log what was sent back and forth and check if you didn't get the full chain, or maybe the wrong chain. Happened to me too. Python 3.7, you actually get the information automatically, so you no longer have to use the tooling. So before I run out of time, quick look at root CAs. So root CAs are the trust anchors, where they're not sent over the wire, they're inside your operating system and in multiple ways. So on Linux, it's typically a file or directory of certificates and the path is compiled into OpenSSL. Request and pip use certify package to ship their own ones, which is, I don't like it for multiple reasons. I'll show you one in a minute. Windows has its own crypto store. We use a hack to use that Windows store, but it doesn't work always correctly. And macOS has two different ways. If you get the new Python builds, you have to use certified too. And on Linux, of course, you couldn't agree on one path. They're just, depending which operating system you have Fedora or Debian or whatever, it's different paths, yeah. So, you can use tooling to look at the path, but why don't I like certify? You have to keep the certify bundle up to date. And to show you one bug, so the first one in public, I found that a couple of weeks ago with New Relic. They had very old CA certs in shipping with New Relic. And some of them were, I think, from 2005, 15, 14, very old. So Peter will send me from stage in a minute. So, okay, I think I have to wrap that up. Sorry, I had 1 minute more. So, hostname verification. You'll have to verify the host name, which is very hard. So please don't do that yourself, and just use the libraries we had shipped. That one issue I found a couple of months ago on LibreSSL. I just skip the cap content, and that one, and TLS 103. So, how to debug one. Yeah, these tooling help, update to Python 3.7. There are a couple of very cool websites you can use. Also, SSL Labs is very useful, and both of these books, especially the Bulletproof SSL and TLS, is fantastic. And yeah, that's it.
Thank you.
Yeah.